Welcome to this session. This session, we are going to prove that if we have a set of real valued functions defined on an interval AB, open interval AB, then this set of functions forms a vector space under the usual addition and scalar multiplication. So here is the proof. So proof. So we say let F, G, and H be functions in this set F of continuous real valued functions in the open interval AB, and let alpha and beta be real numbers, and let plus and this notation be a binary operation for addition and multiplication. Respectively. So we have to go through all the 10 axioms that specifies a vector space. So the first one, we have to test closure with respect to addition. So because we have already specified that F and G are functions in the set of all real valued functions in the open interval AB, then F plus G, this is how we define the function of sum of two functions. And then this is the same as F of X plus G of X. And then this is always a function within this set. The reason, then you say for all X in the open interval AB. So this is to say the sum. So because the sum of two continuous functions because now remember these three dots, when you write three dots in mathematics, this means because. And when you write three dots in this form, this read as therefore. So we are implying this because the sum of two real valued continuous functions in the interval AB is also continuous. So therefore, closure with respect to addition holds. So that's the first property. Second property, we prove commutativity. Now let F and G be in this set F as given. Then F plus G is defined as F of X plus g of x. And then we can write this one as g of x plus f of x reason commutativity holds for real numbers. And so this, from this step, we'll have if f plus g is written as f of x plus g of x, then this one is the same as writing g plus f of x. So i.e. f plus g of x is the same as g plus f of x, which implies that f plus g is equals to g plus f. And this is what shows commutativity. So therefore, commutativity with respect to addition holds. Number 3, we prove associativity with respect to addition. This one we say, let f, g, and h be real valued functions defined in the open interval AB, then f plus g plus h of x will be given by f plus g of x plus h of x, this by definition. And then this one, you also define it as f of x plus g of x plus h of x. And then we can write this one as f of x plus g of x plus h of x. And then I change now the location of the brackets because associativity holds for real numbers. So this one you're saying this operation is valid because by associativity of addition on real numbers. So remember this and this, all these are real numbers. So we'll have, from this one, we have f plus g plus h and then we write here. Remember, we have f plus g and then plus h. So this is the same as writing f plus g plus h of x. So f plus g plus h, i.e., so remember this is for all x in the open interval AB. So that is saying f plus g plus h is equals to f plus g plus h. And you see this is the structure of associative property. So therefore, associative property is defined for addition, or simply associative property holds. Number 4, we have to test additive identity. Now let us note the function be the function whose value is 0 for all values of x in the open interval AB. Then for a function f in this set F, we have f plus this function would be the same as f of x plus 0 of x, and then this would be the same as writing f of x plus 0, and then be the same as f of x. So f plus 0 so i.e. f plus this 0 function, we get f. So therefore, additive identity exists in this set of real valued functions in the open interval AB. Number 5, additive inverse. Does additive inverse exist? So let f be a function in this open interval AB, then negative f of x exists in this set F such that negative f of x is this same function in this set F. And then when you say f plus negative f of x, this will give us f of x plus minus f of x so we have this. So which implies that f plus minus f of x will be f of x minus f of x, and f of x minus f of x is 0. So f of x, so you can simply say f of x plus minus f of x is simply a zero function. Therefore, additive inverse exists in f. Remember, this is for all x values in the open interval AB. Then additive inverse was number 5. So number 6, let's see scalar multiplication. So it specified our scalars to be alpha and beta. So number 6. A closure with respect to scalar multiplication. So let's see whether this set F is closed under scalar multiplication. So let alpha be any real number and F be a function in this open interval AB. Then alpha times F of x actually should be a function in this set, since closure with respect to scalar multiplication holds in R, or this is now just a real valued function within this interval. So i.e. closure with respect to scalar multiplication holds on this set. And then number 7, distributivity. Now let f and g be two functions in this set F, and alpha be any real number. Then if we say F plus G of x be the same as alpha into F of x plus G of x. And since associativity, this is real number, associativity holds in R, then this is the same as distributivity holds in R, then this is the same as alpha F of x plus alpha G of x, which is the same thing as writing alpha F plus alpha G of x. I remember we came from alpha F plus G of x. So this implies that alpha into F plus G is the same as alpha F plus alpha G. And this is the distributive property we were to prove. So therefore, distributive property holds. Actually, to be more specific, you can say left distributive property of multiplication over addition holds for this given case. Number 8 is still on distributivity. So here we let f be the function in this set and take alpha and beta be two real numbers. Then if we take alpha plus beta multiply by f of x, this will be alpha f plus alpha f of x plus beta f of x, which is the same thing as alpha f plus beta f and then of x. So this is f. So alpha plus beta f of x. So this means alpha plus beta f equals to alpha f plus beta f. And actually this is what we want to prove. So distributivity also holds. So therefore distributivity holds in f. Remember this for all x value in the interval AB. And then number 9, associativity with respect to scalar multiplication. So we'll say let alpha and beta be any real numbers and f be a function in this set capital F. Then when you say alpha beta multiplied by f of x is the same thing as saying alpha beta f of x, as since associativity holds in R. Now this can be written as alpha into, so beta f of x can be written as beta f and then of x. So it means we have alpha beta times f of x is giving us this result. This is to say that if you take alpha times beta, you multiply by f, then you get alpha into beta times f. And this is the property that you wanted to show, that you can always have associativity with this scalar multiplication. So therefore, associativity with respect to scalar multiplication holds on this set F. And lastly, number 10, existence of unity in this set. So let 1 be an element in R and F be a function in this set. Then when I say 1 times f of x, I'll have 1 times f of x, which are the same as f of x, because 1 and this are just real numbers. Product of real numbers is a real number. So therefore, 1 times f is the same as just f if you relate this and this one here, i.e. unity in f exists, or to say that scalar identity multiplication is defined on this set F. So because all the 10 properties of 10 axioms of the vector space are satisfied, then the set AB is a vector space. So that is how we prove that. Thank you.